The purpose of this particular session is to introduce you to something called Feynman diagrams in the context of many body theory or finite temperature field theory. So, the purpose of these diagrams is essentially to incorporate the effects of many body correlations into the theory and in the calculation. So, how is it usually done? So, we start with something like a closed line that is punctured by a wavy line at one place, then it comes as a next image, then comes the third one, and so on and so forth. Each power of insertion of this line introduces an additional factor of the coupling constant, let us call that G. So, this particular diagram contributes to the theory to some correction which is of order G. The next one adds a correction which is order G square, the third one of order G cube, and so on and so forth. If the magnitude of this quantity G is much less than 1 and nothing in this loop contributes so much that the power total contribution from this diagram becomes neither equivalent to the second one, rather less than the second one, then we can forget about the inclusion of these higher order terms and be contented with the correction to order G square to our original Lagrangian and carry out the investigations those are needed for our calculations or finding out the observables. Now, in most of the cases, the first diagram that we have drawn over here don't contribute. So, the one that becomes significant in contribution is the one that I have retained in this particular picture. So, to give the kinematical description to this particular diagram, let us denote the momentum that flows into the diagram from left and the momentum that flows out of the diagram from right. We denote them by K. The loop that we have drawn over here with a arrow carries a momentum which is equal to P. The moment it reaches this particular vertex, it acquires the momentum from the external line and the momentum over here becomes P plus K. P plus K, and from this particular end, this outgoing particle, which is a photon over here, actually carries that momentum out. These two vertices that we have where the external line joins the closed loop are called the vertices. For the kind of, as I have just drawn in the figure, in the loop that I have drawn, the loop particle that comes from right carries a momentum which is P, then it picks up a momentum of K from the photon which is coming from the left side, and then it flows inside the loop with a momentum P plus K, and it relieves its momentum at the vertex nu, from where the outgoing photon takes the momentum k and it goes out. Now, this kind of diagram in the theory of finite temperature field theory are usually called Feynman diagrams. Now, this particular structure that I have drawn over here, its name is self energy correction to the photon, and it takes into account medium effects, that means number of particles in the system and temperature and the momentum that these particles are carrying. And at times these are denoted by this particular quantity pi mu nu, and the argument can be something that is a Lorentz scalar constructed out of the variables those are there in the system and the coupling constant and the chemical potential and temperature. If it so happens that this particular phenomena or effect is happening in an external field or something like that, then one should also consider the effect of the field while estimating this quantity that we have written here as pi mu nu. So, this is the lowest order to which the effect of medium, the effect of temperature and the external particles contribute to the Lagrangian of the system, and the Lagrangian in this case can be written as L equal to minus 1 by 4 f mu nu times f mu nu plus a mu times pi mu nu k square and a nu. The higher order terms, order g cube onwards, are essentially dropped. In the next few minutes, what we will do is we will try to tell you under what condition the contributions coming from these higher order diagrams that I have shown can contribute something which is finite to the Lagrangian. I have written L, or they can't contribute anything to the Lagrangian that we have defined by curly L. At times, this quantity curly L is also called as effective Lagrangian or L effective, because it takes into account the effect of the medium and higher order correlations into the description of the system, and it includes the contribution that comes from the vacuum plus the medium ones. Since the objective of this particular course is to expose students and participants to waves, oscillations and directed vibrations in a system, so it is necessary to understand the underlying principles of including all these quantities for the description of the system. Thank you.